One of the most intriguing results from this paper is how multimodal large language models, or MLLMs, struggle to spot the same object or attribute when it's viewed from different angles. For instance, they might have a hard time figuring out if a person in a red shirt is the same one across multiple camera views, almost like trying to recognize a friend in a crowd from a blurry photo taken from the side.
That's a great point, Ben. To achieve this result, the researchers created All Angles Bench, a benchmark with a bunch of real-world scenes and questions that test how well MLLMs can match things up across views. Think of it like a puzzle, where you have to connect pieces from different perspectives of the same room. One view might show a door half hidden, and another shows it fully. They used over 2,100 human annotated questions to simulate this, focusing on tasks like attribute identification, which basically means linking visual traits consistently, no matter the angle.
Building on that, another fascinating outcome is that these MLLMs really falter when dealing with partially occluded objects in different views. It's as if the models get confused when something is blocked in one shot but clear in another, leading to errors in tasks like object manipulation or tracking movement across cameras.
Exactly, and the method behind this involves setting up scenarios where models have to predict or describe actions, like imagining a person walking from one view to another. It's similar to playing a video game where your character moves between rooms, but the game only gives you snapshots from various angles. The benchmark includes questions on relative direction and distance, helping to reveal how MLLMs try and often fail to maintain a mental map of the scene, much like how we humans use our spatial awareness to navigate.
Shifting gears, the paper also highlights that MLLMs aren't great at estimating where cameras are positioned relative to each other. For example, if you shuffle views of a scene, the models struggle to reorder them logically, like figuring out the sequence in a panoramic photo.
Right, to get to that result, the researchers designed tasks specifically for camera pose estimation. Imagine you're directing a movie and need to align shots from different cameras. The benchmark throws in questions that force models to think about the 3D layout, almost like piecing together a 3D model from flat photos. This tests the model's ability to handle geometric consistency, which is crucial for things like navigation in real-world settings. But it shows MLLMs often treat views as isolated snapshots rather than connected parts of a whole.
And one more key finding is how MLLMs perform across other tasks like counting objects or determining relative positions, where they consistently underperform compared to humans, especially in complex, multi-view setups.
To explain that process briefly, the benchmark covers a range of question types, from simple counting, like tallying items in a room from varying angles, to more intricate ones involving object relationships. It's akin to looking at a sculpture from all sides and describing it accurately. The models have to synthesize information, but they often miss the bigger picture due to limitations in cross-view correspondence.
In wrapping this up, the paper's big takeaway is that while MLLMs are stars at high-level reasoning, they need a lot more work on multi-view understanding to become reliable for real-world applications, like robots navigating spaces or virtual assistants interpreting 3D environments.
Absolutely, Ben. Overall, All Angles Bench exposes the gaps in MLLM's abilities, emphasizing the need for better ways to handle 3D scenes and viewpoints. This could lead to future improvements, making these models more human-like in perceiving the world from every angle.